Good morning, everyone. I'm Junichiro Kawaguchi from Japan. My talk on today is a high-density cold gas jet propulsion system for interplanetary propulsion. What do you call it? This is the small RCS reactor control system. It's featured as a cold gas propulsion system. But the cold gas propulsion system are frequently used for the missions that require small momentum. Cold gas propulsion system are supposed to build and simple and low cost. However, they have the big drawback that natural gas is extremely limited in scope, accompanying a huge amount of heavy gas vessels tanks, since the propellant is stored in gas. The simplest way to overcome this difficulty is carrying the propellant in liquid state to vaporize it aboard. That sounds very simple. However, it does not work so simply as expected. 7 years before we launched the world's first solar cell spacecraft Icarus, it carried a liquid gas equilibrium reaction control system aboard. So liquid gas equilibrium RCS actually worked. However, the operation was restricted into small piecewise thrusting only, since the propulsion had to await for the boiling to finish. Okay. So this is the typical configuration configuration of the left block diagram. The HFC is contained in the tank, and it's usually is in liquid gas equilibrium state. It uses an HFC, hexafluorocarbon alternative from gas as propellant stored in the tank filled with a formed metal to retain liquid, also to help get vaporized by metal's high heat conductivity. So whatever the other methods, which is better, equilibrium vapor is a highly humid gas and easily decondenses back. So boiling is very inefficient process due to the degraded heat conductivity, since the liquid becomes full of a lot of bubbles in it. So boiling never finishes quickly. It takes a lot of time. Besides that, the heat utilization efficiency is also very low. So solution lies in producing gas through supercriticality. This is common to make in power plants on the ground. They first pressurize water beyond the critical pressure, and then heat is applied to make water reach to supercriticality. So what is produced via this method is the completely dry gas, not a humid gas. So that is allows the continuous thrusting. This is the very simple the phase transition chart. Vertically pressure is taken, the horizontal the temperature is taken. This point this is not working. This point is this one. Okay, this one is this point is critical point. And suppose under the initial pressure temperature is here, the liquid state is liquid state, and after that, when we pressurize the water and liquid to, and the pressure is raised to high your critical point. When heat is applied, the heat exchanger, the state reaches to the supercriticality point here, and through the expansion nozzle, we can have a dry gas, dry cold gas here, whose temperature is same as the initial temperature here. So this process, it's a really long way. However, when you think about from this point to this point, the state must go through go across a vapor pressure line. That the inevitably faces the boiling the problem. But through this long way that we can avoid that vaporization of the boiling effect, and that's a very efficient process. So the problem is how to pressurize from here to here on the small spacecraft. That is left for the problem. However, we devised the special charger device. That is what we want to talk about today. It's simply the liquid first storage here. That is heated up by the heat exchanger here, and we can have the dry gas here contained in the gas bottle. And that gas returns back to repressurize the liquid again by this and the pressurization device. This is what we call the charger device. And the important thing is that no power is required. It's a passive device and no power consumption. But this acts, they like on a pump, to pressurize the liquid to the very high ultra pressure, using the gas that is produced by the original liquid. So now that we have the new small satellite reactor control system, it's a high density momentum reactor control system carrying liquid instead of gas aboard. And it's a oil-free vaporization mechanism throughout the supercriticality. And it's a pumpless feedback system making use of the charger device newly invented, and no power is required. And it's capable of maintaining pressure even from the blowdown system. And provides a continuous vaporization with heat exchanger aboard, acting like a solar electric or the solar charging system. And low pressurized system and reliable, safe, and low cost system. And it's a regulator-free system. The system itself works as a regulator. Okay? And small minimum impulse bed is provided properly. The property is provided, automatically provided. Think about the high pressurized and the blow gas system that produces a significantly high thrust at initial. However, at the end, the blow gas system cannot provide the large big enough thrust. This system is regulator free, but maintains a continuous thrust. So this is fits for good for small satellites probes in higher orbits of the interplanetary probes. So here is given that one example that we suppose that the 50 kilogram satellite is a 5 centimeter spacecraft, and when you think about the impulse requirement of 100 meters per second, we should look at how the system is developed. This corresponds to the 2 meters per second delta V. A later example shows a 5 meters per second delta V for the system. Then note that even a few meters per second delta V capability enables the 2 be positioned to the constellation position. So this makes opens the door for the small satellites to have business. So typically, when we think about the GN2 of the configuration, because the ISP is probably 60 and 80 seconds, and the mass of the propeller is probably 160 grams, and the corresponding the mass, gas bottle mass is about 1.2 kilograms. The other idea is that the use of the gas helium, because the 160 or higher, and the mass of the propeller is very significantly small. This is the advantage. However, the internal that requires the double the gas bottle mass, so that is not in the end that is not an efficient way. So in this the configuration, suppose that the LCO, so liquid CO2 is used for this charging device system. Thus the ISP is significantly low, and the mass of the propeller is really high. However, the gas bottle is can withstand that's bigger pressure, and the gas bottle mass is very small. And in the end, the system is built in lower mass. The HFC is same. The ISP again much smaller than the gas helium, but then the mass of the gas bottle is a significantly lower, also ignorant. Okay, in that case, the mass for the total system is reduced. That's the advantage of this system configuration. And liquid and nitrous oxide, we may be present liquid CO2, but we have an alternative with the propulsion. This kind of a markup is available on the first floor. When you have the dimension of you just right for looking at and take a look at this model. So let me summarize some of the applications. Contemporary small satellites aim at constellation of formation. And however, the challenge is how propulsion means can be prepared for those low-cost satellites. Cold gas system is sometimes adopted. However, the cold gas system is not appropriate for orbital control of delta V owing to its low impulse. So the amount of gas carried is very much limited. So delta V expected is not much, only a few meters per second, and it expands the business significantly to the constellation flights. And carrying the liquid instead is one solution. But how vaporization produces non-saturated dry gas remains a problem. So vaporization should avoid boiling to keep a high heat exchange rate. And the solution is provided here. This utilizes a super criticality, taking the advantage of self-pressurization technique not always required. So the total the orbital control capabilities provided for those satellites in low cost. Here's another one that we comparison with the hurricane tracker small satellites on the SD5 in the propulsion system. HDCGJ, our propulsion system, weighs a little heavier than that aboard SD5. However, let me note, HDCGJ has advantages in lower pressure, the smaller impulse bit thrust, and the automated and the passive radiation is possible, and no regulators aboard. And no latching valve is required, okay? And no internal leak concern. Okay? So those are the advantages of our system. And then we also add that the low phase transition heat power is also the big advantage. And no sloshing motion, since the regulators contain a pressurized way that in the no sloshing motion occurs. And it can assure a very important point, burst factor of 4 for the tank before activation, so satisfying a launch pad regulation for secondary payload. Secondary payload, once they place on the launch vehicles, and no one can work if that is pressurized. However, this system guarantees that the burst factor of 4, that probably in most cases and comparable for the task of work around that pressurized volume. So this is a secondary advantage. Here is given that the typical example of the BBM and the mock-up. In this case, the specific impulse is available at about 40, and the required the thrust is 120 milliNewton, and the pressure ratio of the charger device is 2.5. The pressure is the ratio from 1.4 megapascal to 3.5 megapascal. Total mass flow rate and expected, the mass flow rate expected. 12.34 grams per second, and the required heat of power theoretically is required power at 21 watts, 21 watts to 25 watts. So we built the BBM mock-up, and that was tested inside the dark chamber. This is a configuration of that. And here's the result. The liquid pressure here is maintained by the controlled and active valve of operation to the 3.5 megapascal. According to the signal, the commanded, and here's the mass flow, maintained at the almost constant, and the thrust, that is almost constantly maintained throughout the performance test. Okay. And the heat exchange beam test result says assuming 120 milliNewtons, theoretically we expect that the mass of the power required is 21 watts. And the experimental result is converted to almost the same as 21 watts. And at this moment, the heat exchanger, the efficiency is not so optimized. It's still 60%. That is 35 watts. The 100 milliNewton is thrust is produced. Okay. Well, this is the compensation for latency and the energy. So this is the really small and can fit for the small rockets. So we have built already the fabrication with the 50 kilogram satellites and the system. This is really the diagram of it. And also that we are still we are doing under the development of the 1U class and the thruster unit. That mock-up is also available on the first floor. So the 50 not only 50 kilogram and the mock-up, and also the 1U class and the propulsion system mock-up is under development. This shows that the actual form of the propulsion system, we developed so far. This consists of the two, the charger units, and it's a typical size of 50 centimeters, the thickness of 115 centimeters. And that can carry up the 250 Newton second impulse that's converted to the 5 meters per second delta V. And this engineer model weighs not optimized, but approximately weighs about 5 kilogram drive. And delivery is ready in a few months, and we can take orders from potential customers. Okay? And let me put another some remarks. Liquid can be replaced by the nitrous oxide N2O. Okay? N2O has almost very similar characteristics to carbon dioxide. Then the system can be built in a same manner, so that is by the supercriticality driven by self-pressurization charger device. And there is a catalyzer available for disassembling N2O. And N2O has a stable liquid, even in very cold temperature, and good for storage. And N2O, when disassembled, it produces this extraordinary heat energy and useful propulsion. And the N2O has another advantage over hydrogen in terms of non-toxicity. The world looks at the substitute for hydrogen, and N2O is one of the candidates. And we performed the catalyzer thruster experiment by the vacuum chamber. As a result of that, the N2O is successfully disassembled, and the temperature rate that goes up, it reaches to 900 Kelvin. In this case, the temperature was intentionally suppressed below 900 degrees Kelvin, so that even the stainless steel will hold with steel. Okay? When we use the high temperature material, that works. The performance is very high. However, that is very expensive. Okay? But in our case, this leads to the low cost of the realized hot propulsion system. The catalyzer was made of rhodium, inexpensive made of metal. So this is one application. This is the final slide. This is an N2O catalyzer thruster, the supercriticality thruster. The N2O is applied for propulsion. There is a problem. So currently, the catalyzer works good for N2O only in gas state. Okay, so it does not disassemble N2O in liquid state so quickly and so efficiently. So that means that we need to vaporize an N2O continuously. So our system at HDC that a high density cold gas system fits for that. Okay, and there is a solution. As I said, producing gas N2O, state gas N2O by this technique powered by solar power solves the difficulty. Combination of this technique and the supercriticality N2O catalyzer system it provides a high specific impulse of the propulsion system. So this is equivalent to ISP that reaches approximately 200 seconds. Okay? And the provision of the gas state N2O chamber enables high efficient propulsion and also faster propulsion with quick response. So this is also applicable for delivery in small low-cost satellites. So again, at the end, I have to say that the delivery is ready in a few months, and we can take orders from potential customers in the world. Thank you very much.
We'll take some questions.
Really interesting talk. I was wondering if there's what's the rating of the charger? Presumably it oscillates back and forth quite a few times. How many times are you currently reading?
This system behaves like in one-way direction. Okay. This is not the basic way. Okay. You see, as that means that if the life of orbit is 10 years, okay, from 10 years, the piston moves from this to this end. That's it. It's a pretty static device.
Oh, okay.
Okay. Right. No wonder about this is basically a vibration problem.
Any further questions? No, in that case, let's thank our speaker.